Hello, audience. In this video, we are going to talk about multi-class sentiment analysis. We are going through the introduction, background, methodology, experiment, discussion, and conclusion. First, sentiment analysis is the process of using natural language processing and machine learning techniques to analyze and determine the sentiment or emotional tone expressed in text data, such as social media posts, reviews, or customer feedbacks. So why is it so important? We all know that understanding emotions isn't just essential for our own development. It's also important for AI, enabling the emulation of human-like intelligence and the detection of public sentiments across domains such as social events, politics, marketing, and product. It is also a challenging thing to do. Research on multi-class in 2017 suggests that one of the biggest challenges is the existence of multiple sentiments within the same sentence. For example, in this word onset, we can find that there are many multiple sentiments here, and it's hard to determine for AI. As we dive into the sentiment analysis, we uncover its fundamental components: natural language processing, text analysis, and computational methods working to automate sentiment extraction or classification from reviews. The workflow of sentiment analysis unfolds in 5 critical steps: data gathering, text processing, feature extraction, sentiment classification, and performance evaluation. In the background, we have multiple methodologies within the field of sentiment analysis, each offering unique insights and challenges. We have applied the lexicon-based approach, machine learning approach, and hybrid approach. First, the lexicon-based approach. It is good for its efficiency in sentence and feature-level analysis. Operates as an unsupervised method, sidestepping the need for training data. However, it is also limited by the domain dependency, where the sentiment of words can vary across contexts, stopping accurate emotional analysis, particularly in cross-domain textual data. In contrast, machine learning algorithms present other strategies for sentiment classification, embracing both supervised and unsupervised learning strategies. Using algorithms like native Bayes, support vector machine, and logistic regression, this approach navigates the complexity of sentiment analysis, enabling comprehension and classification across diverse textual datasets. Furthermore, the hybrid approach bridges the gap between machine learning and lexicon-based methods, combining the advantage to better detection. By integrating sentiment lexicons with statistically and knowledge-based techniques, this approach refines sentiment analysis, broadening its applicability and enhancing accuracy across domains. After background introduction, let's move to the methodology. The dataset we choose is loaded from CSV files containing training, validation, and test sets. A preview of each training data frame DF is shown, displaying the first 5 and last 5 rows of the dataset. It confers the process of 2 columns where sentence contains text data and label contains the corresponding emotion or sentiment labels. The data frame contains 16,000 rows, indicating a substantial dataset size for the text at hand. First, for the data pre-processing, we do the job of text cleaning, tokenization, and stop words. The output demonstrates the text pre-processing on example sentence. After cleaning, the text reads it is an example sentence. Upon tokenization, the individual words are listed, like this is an example sentence. The final output shows the filter tokens. After removing stop words, This pre-processing is fundamental for any text-based machine learning or deep learning model, as it normalizes the input data, allowing for more accurate feature extraction and model performance. Text cleaning is also using a function called text clean text. It's defined to perform text cleaning by removing special characters and punctuation and converting all text to lowercase. This standardization helps in reducing the complexity of the text data and adds in the consistency of the analysis. Second, for the tokenization, we use another function called tokenize text. It's defined to tokenize the cleaned text. Tokenization is the process of splitting text into individual words or tokens. Stop words loading. This is the code loads a list of English stop words from the library. Stop words are commonly used in words in the language like this, is, in, that are often removed before pre-processing text data, as they usually contain little value for understanding the sentiment or emotions of the sentence. We also did data balancing. It is to equalize the representation of each emotion in our datasets. First, we eliminated the surprise character category due to its low frequency. We then processed to reduce the number of samples in the joy, sadness, and anger categories. This prudent pruning was guided by the need to retain sufficient data for model training while striving for balance across the remaining categories. In the slide, you can find that there are several pie charts. They are corresponding to the training, validation, and test dataset post-balancing exhibited the following distributions. The model training was carried out over 25 egg picks with a batch of size of 256, indicating a substantial training string that balances computational efficiency with the need for model coverage. The training process utilized both training and validation datasets to not only feed the model parameters, but also to help them for better generalizations. Our experiments utilize a dual-branch multi-output convolutional neural network, enhancing traditional CNN architecture by incorporating two parallel processing branches and multiple output layers. This algorithm uses separate embedding layers to convert textual data into dense vector. It is followed by a conventional layer to capture local features. Batch normalization and activation enhance learning dynamics. The network analyzes different feature sets, merging distinct strings before distributing them to multiple output layers for comprehensive analysis. This architecture enables non-sentiment interpretation and the detection of multiple sentiments within text through customized multi-output layers. This layered approach allows detailed analysis, effectively categorizing complex emotional states and opinions.
Now, let's move on to how we conducted our experiments. Throughout the experimentation stages of our sentiment analysis project, we have undertaken rigorous model training and evaluation to ensure the highest level of accuracy and efficiency. We have conducted our training over 25 epochs with a batch size of 256, resulting in a commendable training loss of 0.08 and a validation loss showing a consistent downward trend. Our model has yielded high accuracy scores of 0.99 on training data and 0.93 on testing datasets, which is a testament to the robustness of our training regimen. Delving into the architecture and compilation of the model, we've seen that the performance improves as the loss decreases with each epoch, with the lowest validation loss observed at epoch 25. This trend is mirrored in the position and recall metrics, with both showing excellent results over time and the best epoch for validation position peaking notably at epoch 11. Finally, our test evaluation has applied the macro averaging method, giving us a holistic view of the model's performance across all classes. Despite potential class imbalances, the results have been remarkable, with a test accuracy of approximately 0.93 and position and recall both closely aligned at 0.93 and 0.94 roughly. This comprehensive approach to our model's testing and evaluation phases underscores the accuracy and reliability of our sentiment analysis tool. Now it's the discussion. In our sentiment analysis model's continuous improvement process, we integrated the surprise emotion and retained the model. This inclusion only slightly adjusted the model's accuracy to 92%, position to 90%, and recall to 93%. Confirming the model's robustness, this robustness is crucial for nuanced sentiment analysis in various applications. During our analysis, we have observed an unusual occurrence where the recall and accuracy values were identical when using the weighted averaging method. This was tracked back to the balanced distribution of our dataset, where this method gives a balanced representation of each label's true positives, emphasizing the importance of dataset structure in machine learning outcome. Now is the conclusion. To wrap up our presentation, the performance of our emotion classification model is highly commendable. Even with the inclusion of surprise emotion, the model sustains high accuracy, precision, and recall across all categories, signifying its reliability in understanding a broad spectrum of emotions. This level of robustness in our model demonstrates its significant potential for applications in environments where nuanced emotion interpretation is vital. The model's ability to maintain high metric scores across various emotions showcases its practicability for real-world scenarios, where understanding the full range of human emotion is crucial. And that's all for our presentation. And thank you for listening.